Hi, my name is dr. Ahmath. In this video lecture, we are going to continue our discussions about the applications of derivative. In particular, we are going to talk about your favorite topic, which is the Lopitas Rule to find the limits. So to find the indeterminate forms of the limits. So we say that the limit is in the indeterminate form if we've got the limit in the form of 0 over 0, or infinity over infinity, or 0 times this infinity, or 0 in the power of is 0, or 1 in the power of infinity, and so on. So we are going to define what is exactly the indeterminate form of limits, and we are going to learn what is the Lopitas Rule, and we are going to do a couple of exercises on this. And at the end of the lecture, I will give you a small historical story about the invention of this rule. So suppose that we would like to understand the behavior of this function near x is equal to 1. So the ln of x divided to the x minus 1. So we know that this function is not defined for the x is equal to 1 because the denominator becomes equal to 0. Then why don't we just find the limit of the ln of x divided to the x minus 1? The problem is the numerator is still 0. If the numerator would be a finite number, then we could probably find the limit would be simply infinity, for example. The problem is the numerator is going to the 0, and denominator is also going to the 0. So we've got the form of this limit 0 over 0. So we are going to call this type of the limits as the indeterminate limits. So we are going to define this. So in general, if you've got the limit of the form of f of x divided to the g of x, where f of x and g of x are going together to the 0 as x goes to some number a, then this limit is called indeterminate form of the type 0 over 0. So it appears, so here are a couple of examples of the indeterminate limits of this form. For example, x squared minus x divided to the x squared minus 1. When x goes to the 1, so you can just substitute x is equal to the 1, and you can get on the numerator 0 and on the denominator 0 as well. So another example is sine of x over x. It's our favorite example. When x goes to the 0, sine of x goes to the 0, and this is also going to the 0. Or one more example is the ln of x divided to the x minus 1. When x goes to the 1 is also the form of the indeterminate limit of the 0 over 0. So in order to type this kind of limits, we are going to use so-called Lopitas Rule, which basically tells us that if you've got the indeterminate limit of the form 0 over 0, or infinity, then we can evaluate this limit by just finding the derivatives of those functions. So the limit of the f of x divided to the g of x, it is going to be equal to the limit of the f prime of x divided to the g prime of x. So this law is called the Lopitas Rule, and we are going to do a couple of exercises. So let's start from the first one. So find the limit of the ln of x divided to the x minus 1 when x goes to the 1. So we first of all have to check always whether both of the parts of this ratio are going to the 0. So in this case, that ln of x goes to the 0 indeed when x goes to the 1, and the limit of x minus 1 when x goes to the 1 is also equal to the 0, so the requirements of the Lopitas Rule are fulfilled. So that is why the limit of the ln of x divided to the x minus 1 as x goes to the 1 is equal to the derivative of the ln of x. On the numerator, it is going to be equal to 1 divided to the x, and the derivative of the x minus 1 is going to be equal to 1 simply. As x goes to the 1, it is going to be equal to the 1. So it means that the limit of ln of x over x minus 1 is equal to the 1. So let's do a couple of more examples. So I like this example. So e in the power of x divided to the x in the square. When x goes to the infinity, it is going to be another type of the indeterminate limits. It is going to be the infinity over infinity type, right? Because if you look to the e to the power of x, as x goes to infinity, e to the power of x also goes to infinity. At the same time, x in a square also goes to infinity. It is infinity or infinity type of the indeterminate limits. And again, we can use the Lopitas rule. So this is going to be equal to the derivative of the e to the power of x. So which is simply e to the power of x. So this is divided to the 2x. Again, this is infinity or infinity type of the indeterminate limits. So I'm going to use the Lopitas rule one more time. It is going to be the limit of e to the power of x, which is the derivative of the e to the power of x, and simply 2, which is the derivative of the 2x. When x goes to infinity, it is equal to infinity. Well, this limit of the indeterminate form of the infinity or infinity is going to be equal to the infinity. So what I want is, I would like to discuss a little bit more about this limit. So why, for example, the exponential functions are growing much more faster than the power functions. So this kind of functions are going to be called as an exponential functions. Not because there is e on the base, because any function in the form of a in the power of x is called the exponential function, and any function of x in the power of a is called the power function. Okay, so in general, we say that exponential functions are growing much more faster, are reaching the infinity much more faster than x in the square. So in order to explain you what do I mean by reaching the infinity faster, let us look to this example. So let's say you would like to travel from China to US, I think. So and let's assume that I am going to travel to US using the plane, and my friend Murkamal is going to travel to US by riding horse, so from China. So if I'm going to take the train, and when I reach the US, Murkamal is still in the same country, or maybe even in the same region, or even with the same city. This is what I mean that reaching the infinity much more faster than the other function. So the e to the power of x is reaching the infinity much more faster, so infinitely many times faster than x in the square. This is what does it mean that e to the power of x divided to the x in the square is equal to the infinity. So this is just a small example to give you some feelings, to give you some insights about what are the limits. So let's do more examples of the Lopitas rule. So find the limit of the x times to the ln of x. So this is another type of the indeterminate limits when we've got like the 0 times to the infinity limit, right? Because when x goes to the 0, this term going to the 0, and this term is going to the infinity. So what I can do is I can rewrite this limit in the form of infinity over infinity. So I'm going to write this in the form of the limit of x goes to the 0 from the plus. That is going to be ln of x divided to the 1 divided to the x. Now indeed, I've got now the new limit when the numerator goes to the infinity and the denominator also goes to the infinity, because we know that 1 divided to the 0 is going to the infinity. Okay, so we can now apply the Lopitas rule. So I'm going to take the derivative of the numerator, which is simply 1 over x, and the derivative of the denominator, it is equal to the minus 1 divided to the x in the square, which is the derivative of the 1 over x, if you remember. So the derivative of the 1 over x is equal to the x in the power of minus 1, its derivative. So the power minus 1 comes down, it's going to be minus 1 times the x in the power of minus 2. Okay, which is 1 divided to the x in the square was the minus. So we can cancel out some of the x's. This x with this x are going to be canceled out, and this x is going to going up. It is going to be the limit of x was the minus, right? When x goes to the 0 from the plus, it is going to be equal to the 0. Well, this limit is going to be equal to the 0. Again, we found this using so-called Lopitas rule. So let's do more examples. Oh, it is actually the same example. So I'm going to find this limit, which is very interesting. So probably some of you know that this limit is equal to e, right? So I'm going to just try to get whether it is possible to do this. So this form of the indeterminate limit is also, in one of the indeterminate limits. limits. So this is in the form of 1 in the power of infinity, I would say, right? Because you see so that this base is tend to go to the 1 when x goes to the infinity, and the power is going to the infinity. But since this base is not equal to some constant number, because there is this 1 over x there, it is not going to be equal to the 1, right, immediately. Okay, so it means that it is already reaching some number, some constant number, which is e, when the power reaches the infinity. This is what does it mean, the limit of this function. So I'm going to do this. So I'm going to rewrite this form, 1 plus 1 divided to the x in the power of x, in a slightly different form. Okay, I'm going to write as e of ln of 1 plus 1 divided to the x. Okay, this is going to be 1 plus 1 over x, right? Because you know this rule of the logarithms. So the a of the logarithm of the base a of b is simply going to be the b. Okay, and this is all in the power of x. Okay, then I'm going to, and you know that when you are going to powering up the two numbers, right? So they essentially a in the power of x in the power of y, it is going to be simply a in the power of x times the y. And I'm going to just use this rule here. It is going to be e in the power of x times the ln of 1 plus 1 divided to the x. Okay, the reason why I have here is I'm going to find the limit of the power of the x separately. Okay, then I'm going to substitute this. So let's find the limit of x times the ln of 1 plus 1 over x when x goes to the infinity, right? Because we know that by the rules of the limits can go up to the powers as well. So you see, so I've got the infinity, so x goes to the infinity, and this goes to the 0 type, right? So I'm going to rewrite this as the infinity over infinity type of the limit, where I can do this maybe 0 over 0. So I'm going to rewrite this in the form of limit x goes to the infinity, the ln of 1 plus 1 divided to the x divided to the 1 divided to the x. So now this is going to be the perfect example of the indeterminate limit of the type 0 over 0, because when x goes to the infinity, this term goes to the 0 and this term goes to the 0, right? Because 1 plus 1 divided to the x goes to the 1, and ln of 1 is equal to the 0. So I'm going to take the derivative from both of the parts. The derivative of the denominator is going to be 1 divided to the 1 plus 1 over x, right? Times the derivative of the 1 plus 1 over x, which is minus 1 divided to the x in the square. Okay, according to the chain rule. So then the derivative of the denominator is going to be minus 1 divided to the x in the square. We're going to cancel this term and this term out, and what we have here is the limit of x goes to the infinity of 1 divided to the 1 plus 1 over x. And when x goes to the infinity, this term simply goes to the 0, right? And what we have here is simply this is equal to the 0. Oh, 1, sorry, 1. Okay, the limit of the power of the e is 1, so that is why this limit is going to be equal to the e. So do you remember what we started with? So we started with this limit, and this is equal to the e. So it appears this is equal to the e. So I think this is one of the really interesting examples of the Lopitas rule, of the usage of the Lopitas rule, because we know this limit from the definition of the e, right? Okay, so I would like to give you a small historical clue about the discovery of the Lopitas rule. Actually, this rule, the Lopitas rule, was first published in 1696 by Marquis de L'Hôpital, by Marquis L'Hôpital's calculus textbook, which is called Analysis des Infiniment Petits. So, but the rule was discovered by the Swiss mathematicians John Bernoulli a couple of years before this, like 3 years before this. And the explanation is that these two mathematicians has entered into the curious business arrangements whereby the Marquis de L'Hôpital bought the rights to Bernoulli's mathematician's discoveries. So the details included this translation of the Lopitas letter to Bernoulli, proposing the arrangements can be found in the textbook by Eves, which is in the references. So this was like a really interesting story, the historical story about the discovery of this rule, which is very useful, which is very much known by many students. So thank you very much for your attention. I hope that this was very helpful for you.